Some additional logic you might need at the output of our columns is what's called column multiplexing. So recall at the very beginning I mentioned that we might take an array and fold it in order to get good aspect ratio. Let's take a kind of extreme example here. Maybe it's extreme, but if we have 2,000 word lines, but each word line is only 16 bits. So this would be if you just did a 16-bit 2,000 word line, you'd have a really tall, skinny array, which would not be at all area efficient, in addition to the fact that your columns would be 2,000 bits tall, which would be kind of unwieldy and probably wouldn't actually be functional. So we can fold a 2K word by 16 bits into something that looks like 256 rows and 128 columns. But once we do that, we must then, if we're doing a read, we need to select only 16 output bits out of the 128 possible columns. And so in effect this requires 16 8-to-1 muxes. So we'll take those 128 columns and create 8-to-1 muxes that take the right bits from the right columns and send it into an 8-to-1 mux and decide which actual bit comes out. And so that's one of the ways to do that, and we'll go into a little bit of detail on that in the next couple foils. Here is shown what's called a tree decoder mux, which is one possible way to do our multiplexing of our reads. So here we have a column mux where we're only using, instead of using pass transistors, we're only going to use NMOS devices. Again, it reduces the total amount of capacitance, and if we're using sense amps to sense the output anyway, what we can do is we can pre-charge all of the outputs. So we, in the circuit below here is an example of an 8-to-1 mux circuitry where we pre-charge the intermediate values and pre-charge Y and Y bar, and then we have A0, A0 bar, A1, A1 bar, A2, A2 bar are basically our column information of which one we want to send in. We have a tree-like structure where A0 and A0 bar are attached to every other bit for both bit and bit bar. A1 and A1 bar are connected to every other output of the initial two, and then A2 and A2 bar are connected to only one of, or to every other of the A1 outputs, A1 bar outputs. And so in this particular case, with the way this tree structure works, you don't need any external decoder logic. You just need the values of A0, A0 bar, A1 bar, and A2 bar to go in. But it does use a lot of series NMOS devices. Depending on the more depth you have to A0, A1, A2, A3, the more series NMOS devices you have. So it could get potentially a little bit too slow if you have too many of those NMOS devices in series with each other. But this is something that might work for a smaller amount. A0, if you're doing a 4-to-1, 8-to-1, it gets difficult maybe if you're getting more than 8-to-1 or certainly more than 16-to-1. I'm not sure that you'd want to do it this way, but this allows you to pass the value through the series NMOS devices, and then the Y or Y bar value, those are going to your sense amp circuit, and then once that goes to either your sense amp circuit or your write circuitry to write a 0 or 1, then you attach it as normal after that. So in the past foil, showed the tree decoder mux, and while that doesn't require a decoder, it has the problem of having lots of series NMOS gates, which might be a problem with larger decoders. Using this type of structure, single pass gate mux, eliminates all the series transistors, but it does require a separate decoder. In this case, the decoder is similar to other decoders we've seen, where we produce for each of the inputs, A0, A1, A2, we produce the value and the inverted value of all of the inputs, and then we go to 2 input NAND gates if we have 2 inputs, 3 input or 4 input NAND gates if we have 3 or 4 inputs, and then the AND gates will drive a single NMOS transistor for whatever width. If we want a 4 wide or 8 wide mux, we just have 4 NMOS transistors in parallel, or 8 NMOS transistors in parallel. Here they've just shown the Y value, but we'd have a similar thing for Y bar, and we would drive B0, B1, B2, and B3 bar going to the Y bar value, and then those would go down to either our sense amp circuitry or to our drive circuitry for if we were doing a write and driving into the bit cell. So here we're showing an example of just a two-way muxed SRAM. So if we just had a folded by 2, and so we have 2 bit cells, or 2 columns that are next to each other, where we're selecting either one column or the other, depending on whether we're trying to write into column 0 or column 1, which in effect are 2 different words that are folded together. We'll access them through the same word line, but use a different value of A0. So if A0 is 1, we're accessing the column on the left, and if A0 is 0, so A0 bar is a 1, then we're accessing the column on the right. And this is just showing how we're sharing some of the logic for the column logic, and each column still needs its own precharge for bit and bit bar, but we can kind of share the output value of the data, for example, when we're reading out, and we can share the write and write bar values going up to the bit 0 and bit 0 bar and bit 1 bar, or well, this would all be bit 0 of 2 different columns in effect. So it can get a little bit confusing, but in effect you're sharing some logic between in effect 2 different columns that are effectively different words, but they get accessed through the same word line, but are in effect differentiated by a different value of A0. So again, make sure you understand this concept. It's a little bit confusing when you first go over it. Once you kind of go over it a couple times, it gets a little bit easier to keep it in your mind exactly what's going on. Up until now, I've only been presenting single ported SRAM designs, where we're doing only one read or one write on each cycle. But in reality, we have multi-ported SRAMs are needed in a lot of cases for register files and other applications. Just some examples: multi-cycle MIPS must be able to read 2 sources or write a result on some cycles. Pipeline MIPS must be able to read two sources and write a third result on every single cycle, and superscalar MIPS must be able to read and write many sources and results on each cycle. I know for myself, years ago I owned a register file where it was a 6 read 3 write, and so it had to be able to do 6 reads every single cycle and potentially 3 writes every single cycle. And so in order to do that, you need to know how to design multi-port bit cells. So one of the ways to do a multi-port bit cell is to use the same 6T cell that we've been using, but use it in a dual-ported fashion. So the simplest dual port design is the one shown below, where we're using our normal 6T SRAM cell, but instead of having a single word line go in to both NMOS transistors that are on either side of the bit cell, we have a different word line going into each of them and connected. One word A is connected to the right hand NMOS transistor that goes into the right side of the back-to-back inverters, and word B is going into the left side. So doing this, we can do 2 independent single-ended reads. We can't do a differential read, but we can use bit to read out based on word A going high, and bit bar can read out based on word, the other way around. Bit is if word B goes high based on the schematic below, and bit bar is read out when word A goes high. And since we're doing single-ended reads, not a differential read, we need to wait a little bit longer. We need to be confident of whether the value is a 1 or a 0, because if there's any noise, we need to make sure that we have enough of a voltage swing so that we have more voltage swing than any noise that we'd be likely to get. So using this type of design is in general going to be slower than our normal differential read, and so we won't want to use it on a really fast design, but we can use it on a slower design with potentially smaller number of entries, so there's less capacitance on bit and bit bar so that we can get a larger voltage swing over a given amount of time. And using this design, we can do 2 reads at one time, but if we want to do a write, the write still needs to be a differential write, because we can only write into the bit cell if we're driving a 0 on one side or the other, because the 0 can overwrite the value inside, whereas a value of 1, as we discussed before, will not overwrite the values inside the cell. So we need to do since we need to do a differential for the write, we can't do our writes at the same time as our reads. So we could do 2 reads at one time during one phase of the clock, like phase 1, and during phase 2 of the clock, we could do a write into the bit cell using a differential write. If we need to do more than 2 reads in a given cycle or more than 1 write in a given cycle, then we need to do a multi-ported SRAM design. This means adding more access transistors to the design, and of course this is going to add more capacitance to the design, which can hurt some of the read stability, and multi-ported SRAM needs to isolate the reads, because of this, try to isolate the reads from the state node. And so below we can see a design that is multi-ported read and write. You can see the back-to-back inverters are shown with QB and Q, and then back-to-back inverters holding state. And then we have the WW1, 2, and 3, this is a 3 write bit cell. So we have, in effect, our word line values are coming in instead of word line and word line bar. In order to save number of routing tracks, we just have word line coming in, and then we have a local inverter. So you can see WB is our word line bit value 1. So WB1 is our bit line coming in for our write, and it goes to the drain of a NMOS device that is connected to Q. Then it has a local inverter that drives another drain of an NMOS device that goes to Q bar. And so these local inverters here allow us to save routing tracks. So even though they cause a little bit of extra area in the bit cell, once we start getting to multi-port designs, we actually start being more constrained by the number of routing tracks that we need than we do by the number of cells inside of an individual bit cell. Or at least we need to balance the number of routing tracks versus the size of the bit cell and the number of transistors inside the bit cell. So one of the ways to do it with these multi-ported designs, like I said, is to not drive in bit line and bit line bar, but just to drive in one value and then have local inverters. So as far as reading out the bit cell, you can see we no longer directly access the Q and Q bar with the source or drain of an NMOS device and have the bit or bit bar drive the output value onto the read onto the bit line. Instead, we tap off from the Q value, send it to the gate of an NMOS device, and then we have our read word line come in and have another series NMOS in series with the device that's attached to the Q value inside the bit. And then if the value of Q is high and a read word line comes in, like read word line 4 comes in and turns the series device on the far right, that NMOS device is turned on, the Q value is high, read word line 4 is high, that means we'll pull down the value of read bit line 4. And so we get a value of read bit line 4 pulled down. As long as we pre-charge our read bit lines high, then if the Q value and the read word line value both go high, the bit line that was pre-charged will get discharged. And so this allows us to do a read without disturbing the internal value of the bit cell itself. So one last foil here on SRAMs before we go on to a new array topic or new memory topic is, in general, large SRAMs, as a general rule, are split up into subarrays for speed. As I mentioned earlier, when we get into the really large arrays, the larger your bit lines and word lines are, the more capacitance on them. And so at some point it makes more sense to split up into smaller chunks, and then once you read out values to then multiplex them together after they get read out in order to try and distribute your capacitance a little bit better as far as driving your word lines and bit lines. So one example just shown here, the UltraSpark had a 512 kilobyte cache, or kilobit cache, kilobyte. They wound up splitting it up into 4 different 128 kilobyte subarrays. Each of those had 16 8 kilobyte banks, and each bank was 256 rows by 256 columns per bank. And you can kind of see they have the main arrays there. If you look at all the way down to the banks where there's an actual array of bit cells, it turns out that 60% of your area is actual bit cells. 40% of your area is space for all of the control, the word lines, the bit line drivers, the read, sense amps, all of that stuff. And space also in here for tags and additional control logic around it. There's, in addition to your actual array bits, there's a whole bunch of other miscellaneous logic and control and decoders and everything else that you need around the array bit cells. So just keep that in mind. If somebody comes to you and says, "Oh, I have a way of shrinking my array bits by 20%, but it requires an additional 30% in terms of like the decoder logic or other things," turns out might not actually be a net gain. You have to keep in mind both the array and all the control logic around it as when you're trying to optimize for area and speed.